Hey guys, happy virtual day and welcome back to calculus. Almost there for February break. All right guys, so today we are continuing our unit in terms of applications of the derivatives. We are going to continue seeing what can we do with derivatives and what can we use them for. All right, so I want us to actually consider the function f of x equals x cubed minus 6x squared. And I'm going to ask you on what intervals is f of x increasing and on what intervals is f of x decreasing. Now, if we have the graph of the function, which I've provided you with below, we can read this function from left to right to see where is it increasing and where is it decreasing. So as our function increases, we can see, guys, from negative infinity to 0. That is one of the intervals where our function is increasing, because as we read it from left to right, our function is going up. And then we can also see from 4 to infinity that that's another region where our graph is increasing. That's where our graph is going up. And we can see in the region in between from 0 to 4, that is where our function is going down. That is where our function is decreasing. So it's clear that the function decreases from 0 to 4. But you're not always going to be given the graph of a function, so we're not always going to be able to read it from left to right. Sometimes we might have to figure out where is it increasing and where is it decreasing algebraically, right? So that leads us kind of in terms of dealing with this function. Well, how does that relate back to derivatives, right? How does that work with us? Well, we know that a derivative is the slope of a tangent line. So what is happening to our tangent line as we go along this curve? That is the question. What is happening to the slope of the tangent line? So why don't we take this function, put it into Desmos, and let's take a look at the equation of our tangent line, or let's look at multiple tangent lines. So as I go into Desmos, here we have the function we were just looking at. We have the relative maximum there at 0, 0. And we also have a relative minimum there at 4, negative 32. And let's write the equation of the tangent line for any value along the curve. So we'll call it L of x. So again, just indicating the equation of the tangent line. And let's rewrite it using function notation for any value of a. So that means that I can add a slider for a. And we can look at all different coordinates of a. That would be plus, we have f prime, right? Our derivative at a. And then we have to multiply that by x minus a. That would finalize out the equation of your tangent line. And as you can kind of see, as I change the different values for a, that just means that I move along the curve. You can see different things happening to our tangent line as we move along. So guys, first let's focus on the regions where the function was increasing, right? So if you notice here, as I move along in this region, this is where my function is increasing. So my a value is getting closer to 0. Notice that that tangent line, guys, always has a slope that's positive. Okay, the slope of that tangent line is positive. And it continues to be positive, and it continues to be positive, and it continues to be positive until I hit that relative maximum there, right? And now the slope of that tangent line is no longer positive, but rather the slope of that tangent line is actually 0. So we went from a positive slope of a tangent line, right? That slope of that blue line is positive, to now the slope of the blue line, the slope of your tangent line being 0. And then we can see as we move forward, the slope of the tangent line in the middle section becomes negative, right? We can see it being negative as we're tangent in that region. And it continues to be negative as we move through until again I hit the minimum. And as I hit the minimum, now again, the slope of my tangent line is now 0, right? So I went from a positive slope to a 0 slope, to a negative slope, to a 0 slope. And then as we continue through, it goes back to positive. So basically what we're indicating here, guys, is that the slope of the tangent, aka the derivative, guys, as long as the slope of the tangent line is positive, that means that our function is going to be increasing. Notice here, the slope of the tangent line is positive. That's where our function was increasing. In addition, again, here, the slope of the tangent line is positive. That's where our function is increasing. When we're in the center section, that's where our function is decreasing, right? That's where the slope of our tangent line is negative. So we can see the tangent line having a negative slope there. So how do we put this, guys, in terms of derivatives? Well, we just put it in words. We said the slope over here is positive for it to be for the function to increase. And we said the slope of the tangent line would have to be negative for where the function is decreasing. And in order for us to change from increasing to decreasing, right, or for us to have a relative max like that, or to have a relative minimum, so changing from decreasing to increasing, the slope of our tangent line is actually 0, meaning we have a horizontal tangent. So let's kind of put this kind of all together in terms of words and some notes for a second. So if I want to know where a function is increasing, right, that would mean where the slope of your tangent line is positive. That would mean that f prime of x, or the derivative, would have to be greater than 0. In addition to that, if we want to know where a function is decreasing, that would mean that the slope of the tangent line, or f prime of x, would have to be negative, right, or less than 0. So how do we do that algebraically? Well, guys, if you want to figure out where something is positive or where a function is negative, think all the way back to September and October when we did inequalities, right? Remember, we took our function, factored it, put the numbers on the number line, and checked the regions? Well, that is exactly what we were practicing this skill for right here. So guys, if I want to figure out where a function, or where the derivative specifically, so our f prime of x in this case would be 3x squared minus 12x. If I want to figure out where this function is either positive or where this function is negative, I first need to figure out where is this function actually equal to 0. When I factor it, I take out my greatest common factor of 3x. I'm left with x minus 4. And notice our cutoffs here are 0 and 4. So when I go to look at my number line in terms of what's happening to my function, I know that my cutoffs are 0 and 4. That is where the derivative, or that is where f prime of x changes signs from positive to negative. Now we just need to know what are the signs in each of those regions. If you recall, we checked those signs by using a chart. So we had values for x, we had our function, which was 3x times x minus 4, meaning our derivative function, because that's what we're checking the signs for. And then we're trying to figure out what is the sign for f prime of x. Well, in the first region, let's use something like -2. So that's a negative factor in front and a negative factor second. So that is a positive derivative. That means if your derivative is positive, that is where your function is increasing. If we include a number in the next region, we can use something like 1. That would be a positive factor in front. That would be a negative factor second, which is a negative derivative. That would mean that our function decreases. And then from there, we can double check again. In the last region, we can choose a number like 5. We would have 2 positive factors whose product is positive. Therefore, the derivative is positive. So notice we can see that this is where our function is originally increasing, changing over to decreasing, and then we can see that our function is changing back to increasing. And by using this, we can also see where there are relative maxes and relative mins. Notice here, there would be a relative max, right? And when we have a relative max, that is where our derivative, or that is where f prime of x changes from positive to negative. If we have a relative min, right, this would be a relative min, put the word relative in there. We have a relative min, that is where our derivative, right, or the slope of our tangent line, instead of changing from positive to negative, guys, it's going to change just from negative to positive, meaning the original function, not the derivative, but meaning the original function changes from decreasing to increasing. So notice there we can read right from that number line, where is the function increasing, where is the function decreasing, all just from using the derivative and determining where the derivative is positive and where the derivative is negative. Now, if you recall, right? When we did number lines back in September, I said, guys, we have to make sure about sign changes in each of the regions, right? And that's because we want to take a look, guys, at our functions. We want to see, well, maybe there's times where our function is decreasing in two areas or increasing in two areas next to one another. Take a look at what I mean by making this statement. Because let's consider the function x to the fourth plus 4x cubed. And I'm asking you to decide, where does f of x have a relative max or a relative minimum? Classify the coordinate and justify your answer. Now, if we recall from our conversations, it's where the derivative changes signs from either positive to negative or negative to positive. So guys, if you want to have a relative maximum, or if we're going to have a relative minimum, either way, notice your tangent line at those points, okay? Notice your tangent line at those points are going to be horizontal, right? So if we have a maximum or if we have a minimum, okay, that means that our tangent line is going to be horizontal, or we're going to have a horizontal tangent. Because recall from last unit, if we have a horizontal tangent, that means that the derivative has to equal to 0. However, we do need to make sure, we do need to check that there is a sign change. We do need to make sure that the function goes from increasing to decreasing or decreasing to increasing. So let's take a look. If I take the first derivative for this function, f prime of x, that would be 4x cubed plus 12x squared. If I try to set this equal to 0 and figure out where are my horizontal tangents, where do I potentially have a maximum or a minimum, I could factor 4x squared and I'd be left with x plus 3. Notice in this scenario, our values for x are 0 and negative 3. So when I go to my number line, okay, my cutoffs this time are at 0 and negative 3. Oops, put them in backwards order. Negative 3 and 0. Now remember, I'm not checking the signs of the original function. I'm checking the signs of the derivative. The derivative tells me if the function increases or decreases. So here's a number line to check the signs of the derivative. And here's my little chart to check my regions. X values, the derivative, which happens to be 4x squared times x plus 3. And then I want the signs of the derivative. Let's see what it provides. So if I put in something like negative 4, that's my first region, okay? Something being squared is always positive. Negative 4 plus 3 is a negative, so my derivative is negative. That means that the function from here to here, guys, is actually decreasing. And then if I take a look at my next region, maybe try something like negative 2. Again, negative 2 squared is always positive. Negative 2 plus 3 is also positive. So now I have a region that is positive. So now my function is increasing, right? So it seems to go from decreasing to increasing. If I try the next region, let's say something like a positive 2, positive factor, up, another positive factor, my derivative stays positive, which means my function continues to increase. So even though there's a horizontal tangent here at 0, guys, even though there's a horizontal tangent at 0, because that's where the derivative equals 0, note there is no maximum or minimum at 0 because there is no sign change. I'm not going from increasing to decreasing, and I'm not going from decreasing to increasing, okay? So here, when I'm looking at this, there is no relative max. And there's no absolute max because it's a polynomial, so it keeps on going off towards infinity. But what I do see here, guys, is that at this point, we do have a relative minimum, right? We have a relative minimum and negative 3. And if I asked you to justify, okay, why do we have a relative minimum at x equals to negative 3, you're going to say, well, that's because f prime of x, okay, changes signs, but more specifically is changing signs from negative to positive, meaning f of x, the original function, changes from decreasing to increasing. Because they will ask you a lot on the AP to justify why something is a maximum or why something is a minimum. So it is your job to practice writing this explanation, okay? You are going to classify something as a relative max or relative min, and then you're going to say, hey, I showed my work using the derivative, so what about the derivative says minimum? Well, it's the fact that the derivative or the slope of the tangent line goes from negative to positive, meaning that the original function goes from decreasing to increasing. So how does this all play a role in terms of bigger picture things, right? Well, guys, to tie up these skills that we're just talking about here, okay, our goal is to tie it back to what we call the extreme value theorem. Because when we talk about an extreme value, okay, the extreme value theorem, what we're talking about really is like saying our absolute max or min. We want the highest point or we want the lowest point. That's what they're talking about. So the extreme value theorem is an extension of what we were just talking. However, the extreme value theorem says, all right, let's look for absolute maxes and absolute mins, but not looking at the entire function. Let's just look at a small interval of that function. So guys, if I were to look here at this function here, given to you in terms of where the function increases or where the function decreases, right? If I'm looking at absolute maxes and I'm looking at absolute minimums, let's focus first on absolute min, right? If I were to take a look at this graph and I said, all right, let's look at the absolute minimum, okay, from, let's say, from here to here, right? As you're going through, okay, this endpoint here is at that y-coordinate, this endpoint here is at that y-coordinate, but as I compare every other coordinate to that, right, we also have this minimum value here. So the question is, where is the lowest y value? Well, the lowest y value happens right there, right? If I took the derivative, I set equal to 0, I can see that I have a local minimum there, right? Well, what if I changed the interval? What if I changed it just a smidge and I said, all right, well, we'll still start here, right? But now let's go to here. And I said using the blue interval, where is the absolute minimum there, right? So we start here at this point and every point seems to get higher. And now I start to get lower, and here is another point, right, where we end. That is the end point of the interval. Now the question is, which one is the lowest? Which one is the absolute min? And before, when we looked at the pink interval, the absolute minimum used to be at the center, of the interval, but now our absolute minimum is actually right here. It's at an endpoint. So the only difference between what we were doing before in terms of finding maxes and mins, where we're using the sign change of the derivative, we have to use here the sign change of the derivative just like we did before, but we also have to compare it to the endpoints of the interval. Because sometimes you might not get a minimum in the interval, but you'll have an absolute minimum at the end point of your interval. So the extreme value theorem, what it basically says is if we have a continuous function, if our function has values everywhere, it has to have an absolute max and it has to have an absolute min. So things that we need to consider when talking about the EVT. 1, how do we classify maximums or minimums? Maybe we are using our derivative and we're trying to see if it's positive or negative and where it changes signs. The only extension here though is that we are focusing specifically on an interval that we will call A, B. And we just have to compare those maxes and mins on the interval to the values at the end. So let's take a look here. Find the maximum and minimum value of this function on the interval from -2 to 6. So we're going to start this problem off just like we did our problems above. Let's start analyzing the derivative. Let's see what's happening with f prime of x. If I go to take my derivative here, f prime of x, this is 3x squared minus 12x minus 15. If I set this equal to 0 to look for my sign change, I can factor out a 3, x squared minus 4x minus 5, and that can factor to x minus 5 and x plus 1. So that means the cutoffs, or where does the derivative change signs, that's going to be at positive 5 and negative 1. So on my number line, okay, I have here positive 5 and negative 1. Now, the only thing that's going to change here, though, guys, is the fact that I shouldn't have arrows because I'm not looking at the entire function. We're only looking from negative 2 to positive 6. So I'm going to change these endpoints, and I'm going to change this to a solid line to say, all right, I'm stopping at negative 2. To say, okay, I'm stopping at positive 6. I don't want to know what's happening past those numbers. That's specifically what I'm focusing on. And we're going to go back to checking the signs of the derivative, right? So as I'm looking here, again, table of values. Here are my x values. Okay, here's my derivative. I have 3, x minus 5, x plus 1. And I'm looking for the sign of the derivative, so f prime of x. Choose a number between negative 2 and negative 1. So you can do negative 1.5. Okay, we would get a negative factor and also another negative factor, which could give us positive. So derivative, which means our function is increasing. If you were to try a number in the next region like 0, you would have a negative factor and a positive factor, which again gives us a negative derivative. So that means that my function would be decreasing. And then finally, last but not least, in the last region, you could try something like 5.5, which would give you a positive factor and a positive factor, which means the derivative is positive. So in terms of looking here, again, the function is going from increasing to decreasing to increasing, right? We have the middle section here, which is decreasing. In terms of looking at a relative maximum, let's start there. Finding, not a relative maximum, sorry, let me rephrase that to an absolute maximum, because that's what we're looking for the EVT, right? The extreme value, the highest value, the absolute maximum value. If you look at the coordinates here, guys, we do have a potential for a relative max here. In fact, we do, because it changes from increasing to decreasing. But where else do we potentially have a maximum? And if you look here, notice that the function is continuously increasing. It's going up, it's going up, it's going up until we get to 6. So the problem here is if I want to know where's the absolute max, I need to find the value at negative 1. And I need to find the value of 6, and I need to be able to compare them. So if I find f of negative 1, or the y value at negative 1, that is negative 1 cubed minus 6 times negative 1 squared minus 15 times negative 1. So that is equal to negative 1 minus 6 plus 15, or that's 15 minus 7, and that is 8. So that means that the value at negative 1 is 8. Now let's compare that to f of 6. So if I'm looking at f of 6, that is 6 cubed minus 6 times 6 squared minus 15 times 6. Now this is actually on the easier side because we have 6 cubed, and then hidden here we have another 6 cubed. So they actually technically cancel to 0. So we wind up getting a negative 15 times 6. So let's see, that would be 30, 60, 90. So this would be negative 90. So as I'm looking here, guys, which one is higher? 8 or negative 90? Obviously 8's higher, right? So our absolute maximum, okay, our absolute maximum is, okay, oops. I have no idea what just happened to that. Our absolute maximum, guys, is actually occurring at, is occurring at negative 1, and that value happens to be 8. So again, absolute maximum, okay, the absolute maximum is occurring when x is equal to negative 1. And f of negative 1 is actually equal to 8. We would do the same process, guys, in terms of finding your absolute min, except for the fact that when you go to find your absolute min, Okay, that can happen in two other places. So I can see here that, again, relative minimum here potentially at 5, but also need to check this endpoint here at 2 because notice it is lower than the other values there. So let's check f of 5 and let's also check f of -2. So if I take these values, guys, and I plug them into the original function, so let's see, we have, just going to the calculator to make this go a little quicker and to make sure I don't make any mistakes. We have f cubed and we have minus 6 times f 5 squared. And then we also have minus 15 times 5, and that is -100. Okay, and then we're going to do the same thing, but now we have -2 cubed minus 6 times -2 squared, and then minus 15 times -2. So that is going to be -2. And we're going to ask ourselves, well, guys, which one is lower, right? So our lower value here is the -100. So your minimum value, okay, so the minimum value is -100, but if they ask you where is it occurring or what is the coordinate is occurring at 5, comma, -100. Be careful about how they ask you for the question, because they ask you for the coordinate. You want to make sure you provide your answer as an ordered pair. If they ask you for a minimum value, they just want the y value that is the minimum, okay? Or if they ask you for the x coordinate, they just want the x coordinate. So please make sure you are reading the question. But the whole idea about the EVT is the fact that we are still looking for maximums and mins, but we are looking for absolute maximums and absolute minimums, and particularly on an interval, which means that we need to check the endpoints of the interval to make sure that they are not higher or lower than the other points on the function. So again, your EVT. The EVT guarantees both a minimum and a maximum value for a function under certain conditions. It states if your function is continuous on a closed interval, so again, it has to hit A and it has to hit B, we have to include the endpoints, then f of x has both a maximum and a minimum value on the interval A to B. So your job, guys, to wrap up for today is to continue on the next couple of examples. So you are looking at the EVT of finding the maximum on these two functions here. And then for questions 1, 2, 3, 4, okay, you are working on those and submitting them as work. All right. So guys, if you have any questions, please feel free to reach out to me. We will continue working on this as we move through, because please submit your notes as you're going through there. And then your submission of what you are actually doing after this video is to look at the remainder of these problems and have those ready to go as part of your submission. Guys, have a lovely break. Please get some rest. Come back well rested. And I look forward to seeing you all in a couple of Mondays.